Whenever I picture a quantum computer, I have this very, very specific kind of glamorous image in my head.
Oh, the golden chandelier.
Yes, exactly. It's always that gleaming, multi-tiered gold chandelier hanging in some pristine lab.
It is definitely iconic. You see it in literally every press release.
Right. It looks like a prop from a steampunk sci-fi movie. It screams, the future. But I was reading through this stack of research you brought in for today's deep dive, and I had a bit of a realization.
That the reality isn't quite so photogenic.
Yeah. If you actually peel back those gold layers, which are really just the refrigeration unit, and look inside a working quantum processor today, it's not elegant at all. It honestly sounds like a nightmare.
It can be a nightmare, yeah. The reality of quantum computing right now is a lot less about shiny plating and a lot more about managing a terrifying tangle of coaxial cables.
Uh-huh.
It's incredibly messy.
Right. The interconnect bottleneck. That's where we're starting today. Because apparently we have a massive logistical problem if we want to scale this technology for you, the listener. We want chips with millions of qubits, but we're stuck figuring out how to plug them all in without melting the entire system down.
Precisely. Think about it this way. To control a qubit, you need to send microwave signals from room temperature, where you and I are sitting, all the way down to the processor.
Yeah.
And that processor is sitting at about 10 millikelvin.
Which is colder than deep space.
Much colder.
Yeah.
And currently, that involves running a physical wire for every single qubit.
Which, is fine if you have 50 qubits.
Yeah.
You have 50 wires. It looks like a plate of metallic spaghetti, but it's manageable. But 1,000,000 qubits...
You need 1,000,000 wires.
Yeah.
And wires, by their very physical nature, conduct heat. If you run 1,000,000 copper lines down to a chip that needs to stay at absolute zero, you don't have a quantum computer anymore.
You have a space heater.
A very expensive, very inefficient space heater. The fridge just cannot keep up with that thermal load.
So today's deep dive is a little different than our usual fare. We aren't talking about some magical new particle physics discovery or a totally new qubit type. We're talking about the nuts and bolts, the plumbing.
The unsexy stuff.
Exactly. We're looking at 3 massive engineering breakthroughs from late 2025 and early 2026. Our mission today is to understand how we move from experimental physics to reliable engineering.
And honestly, to an engineer, this is the most exciting stuff happening right now.
We've got 3 specific solutions on the docket. First, a team that decided the best way to manage those millions of wires is to use tiny bouncing mechanical switches inside the deep freeze.
Which is counterintuitive, as we'll see.
Right. Then we're going to look at a completely new computing paradigm called entropy computing. It suggests we should stop fighting noise and start using chaos to solve hard problems.
That's the Nguyen paper from October 2025.
Yep. And finally, a new way to tell if your quantum computer is outright lying to you without needing a second, even bigger quantum computer to check its homework.
It's a journey from theory to actual industrial-scale reality.
I love it. Let's get right into the plumbing.
Let's do it.
Okay, so let's start with that wiring nightmare. You mentioned mechanical switches. Now, when I hear mechanical switch, I think of a light switch on a wall. I assume we're talking about something a bit more advanced?
A little bit, yes. This comes from a paper by Lee and colleagues published just last month in February 2026. They are tackling that exact cabling problem. Their solution is something called a cryogenic multiplexer.
Multiplexer. So basically a traffic cop for electronic signals.
Exactly. The idea is simple. Instead of running one wire for every single qubit all the way up to room temperature, you run just a few wires down. Then sitting right next to the cold quantum chip, you have a switch, the multiplexer.
And it routes the signals to whichever qubit needs them at that precise microsecond.
Right. It drastically reduces the number of cables crossing the temperature gradient.
It's like using a power strip instead of plugging 100 different lamps directly into the wall outlet.
But what are these switches actually made of? You said mechanical, and I'm hung up on that.
That's the fascinating part. They use MEMS, microelectromechanical systems.
MEMS.
Yes. These are tiny physical switches with actual moving parts. We're talking about microscopic silicon beams that physically bend up and down to close a circuit.
Wait, actual moving parts at 10 millikelvin? I thought everything practically froze solid at that temperature. I'd expect a tiny mechanical beam to just become incredibly brittle and snap.
That is the standard intuition. Most electronics despise the cold. But here is where it gets really interesting. The researchers tested a specific commercial switch, a single-pole 4-throw configuration, and found that these things actually perform better in the deep freeze.
Better? Well, physics gets a lot cleaner when it's cold. Metal conducts electricity more efficiently. They saw the operating voltage drop by about 3.5%, and the on resistance, which is how hard it is for the current to push through the closed switch, dropped by over 15%.
So the extreme cold basically turns them into super switches.
Exactly. And because the switch relies on a tiny cantilever beam, think of a microscopic diving board that can expand or contract freely, the thermal contraction didn't warp the shape enough to matter. It survived the thermal shock perfectly.
Wow. Okay, problem solved then. We just solder these MEM switches into the fridge and we save the day.
Not quite. There is a but, and it's a really weird physical quirk. It's what they call the bounce.
The bounds.
Yeah. So these commercial switches are packaged with a gas inside the casing, usually nitrogen. At room temperature, that gas provides air resistance. It acts like a shock absorber when that tiny beam slams shut to close the circuit.
Like the pneumatic hinge on a heavy door. It keeps it from slamming.
Exactly.
Yep.
But at cryogenic temperatures, what happens to that nitrogen gas?
It freezes solid. It drops right out of the air.
Right. The inside of the switch suddenly becomes a quasi-vacuum.
Oh, I see where this is going. No air resistance.
Zero. So when that tiny beam hits the electrical contact, there is no cushion at all. It's like jumping onto a bare trampoline. It bounces. The data showed highly unstable signals for about 150 microseconds because the switch was literally chattering open and closed.
150 microseconds in quantum processing time is an absolute eternity. You need precision, not a flickering connection. Doesn't that just scramble the qubit you're trying to control?
It's disastrous. It makes the switch completely unusable for high-fidelity operations. But this is where the pure engineering comes in. They couldn't put gas back in, obviously. Physics is physics.
Yeah.
So they changed how they drove the switch.
A software fix for a hardware problem?
More or less. They developed an engineered waveform. Think of like braking a car at a stop sign. If you just slam the pedal, sending a simple on signal, you skid, you jerk forward. So they used a dual pulse method. First, they send a high voltage pulse to get the beam moving fast. That's flooring the gas pedal. They want the switch to close as quickly as possible.
Okay.
But just before it hits the contact microseconds before impact, they drop the voltage dramatically. They hit the brakes.
So it glides in?
A soft landing. The beam touches the contact with near zero velocity, no kinetic energy left to cause a bounce.
That is incredibly clever. It's exactly like catching a raw egg. You don't hold your hand out stiff. You pull your arm back to absorb the kinetic energy as it lands.
And it was wildly effective.
Yeah.
With this specific waveform, they ran these mechanical switches for over 100 million cycles at cryogenic temperatures with zero performance degradation.
100 million cycles without snapping.
Yep. They even successfully performed NAND and NOR logic gates with them.
Why does building a logic gate out of a switch matter in this context?
It proves deterministic control. If you can build a stable logic gate, you aren't just flipping things on and off arbitrarily. You are performing reliable computation. It proves we can put the complex plumbing for millions of qubits right inside the fridge.
I love that. We fixed the vacuum trampoline problem by tapping the brakes. It really reminds you that even at the cutting edge of quantum mechanics, sometimes you just need good old-fashioned mechanical engineering.
You really do.
Yeah.
And that stark practicality is exactly what the industry needs right now. But I want to shift gears completely for our next paper.
Let's do it.
We've been talking about how to fix the physical environment to make it perfect for the computer. But the ingredient paper suggests maybe we shouldn't be trying to fix every little imperfection. Maybe we should embrace the chaos.
This is the Entropy computing paper. This one really threw me for a loop because it feels like it violates the core tenets of the field.
It is a massive paradigm shift. Usually in quantum computing, noise is public enemy number one. Companies spend billions trying to shield qubits from thermal noise, stray magnetic fields, cosmic rays, everything.
But this paper asks, what if noise is actually a tool?
Exactly. They built a machine they called Dirac-3, and they're very explicit. This isn't a standard gate-based quantum computer like the ones IBM or Google are building.
It's an optimization machine.
Right. It's designed specifically to solve NP-hard problems.
Let's ground that for the listener really quick. What does an NP-hard problem look like in the real world?
Think of complex logistics. Imagine you are a major shipping company. You have 10,000 packages, 500 delivery trucks, and a map of a city with real-time traffic data. You need to find the single most efficient route to save gas and time.
The number of possible combinations is practically infinite.
Trillions upon trillions.
Yeah.
And if you just use a standard classical algorithm, it often gets stuck. It finds a route that is pretty good, and the computer stops looking because every minor adjustment it tries makes the route temporarily worse.
Right, the algorithm thinks it's finished.
In mathematics, that's called getting stuck in a local minimum. Imagine you are hiking in a vast mountain range in completely thick fog. You want to get to the absolute lowest point, the valley floor. So you walk down the slope until the ground starts going up again in every direction.
And because you can't see through the fog, you assume, hey, I'm at the bottom.
But you're actually just in a small crater halfway up the mountain. The real valley floor is over the next ridge, but you lack the energy to climb up and out of the crater to find it.
That makes perfect sense. So classical computers and even standard quantum algorithms get stuck in that crater. They settle for the good enough answer.
Precisely. So how does Dirac-3 solve this? It's a hybrid photonic-electronic system. It uses photons, particles of light encoded into specific time slots, which they call time bin qubits.
Qubits with a D.
Yes, meaning they have more than just two states, unlike a standard qubit. The machine operates in a continuous feedback loop. It measures these photons and it feeds the data back into the system to adjust the parameters. But here is the critical innovation. They rely heavily on quantum fluctuation, specifically shot noise.
Shot noise. That's the inherent randomness of when individual photons actually arrive at the detector, right? Kind of like the sound of rain hitting a tin roof.
That's a brilliant analogy. It's entirely random. Normally, you want a strong signal to drown out that randomness, but in Dirac-3, that shot noise acts like a physical shake to the system.
Oh, I get it. If your solution gets stuck in that shallow crater, the random noise provides just enough random energy to literally kick the system up and out of the hole so it can keep exploring the mathematical landscape.
Exactly. It tunnels out of the local minimum.
It's like shaking a box of marbles. If you just pour them in gently, they snag on each other and get stuck in little bumps. But if you vigorously shake the box, they eventually all settle into the absolute lowest point.
Yes. And here is the truly counterintuitive part of their findings. The researchers discovered that by intentionally using fewer photons, operating with a much lower mean photon number, they actually achieved vastly better answers.
Walk me through that, because fewer photons usually means a much weaker, degraded signal.
It does. But fewer photons means more noise relative to the signal. Go back to your rain on the roof analogy. If it's pouring in a torrential downpour, it just sounds like a constant, steady hum. You don't notice the individual drops.
Right.
But if it's just lightly drizzling, you hear the sharp random impacts. Tap, tap, tap. The fluctuation is much more prominent relative to the total volume of water.
So by turning the system's power down, they essentially turned the mathematical chaos up.
Exactly. And by dialing up the noise, they completely prevented the system from getting stuck. They tested it on a highly complex 50-variable non-convex problem. Dirac-3 fundamentally beat a classical gradient descent algorithm, which kept getting trapped in those local minima.
It also outperformed semi-definite programming on max-cut graph problems, didn't it?
It did, consistently.
That just feels like it breaks every rule of high-performance computing. Usually the brute force classical mindset is, if you want to solve a harder problem, you build a bigger supercomputer and pump megawatts of electricity into it.
It breaks classical rules, sure. But it suggests that energy efficiency and solution quality might actually be deeply linked in these open photonic systems. It implies that being computationally smart and being highly energy efficient are the exact same goal.
That is wild. We normally view efficiency as a pure compromise. You know, putting your car in eco mode makes it sluggish. But here, eco mode literally makes the machine smarter.
It's a total reversal of how we allocate computing resources.
Okay, so we have bouncing switches that thrive in the cold, and we have photonic computers that run on pure chaos. But there is one giant lingering question, and knowing your background in verification, I bet this bothers you the most.
The issue of trust.
Yes. The God complex problem. If I asked a quantum computer to solve a logistics problem that is so unfathomably complex, my classical laptop can't even verify the math, how do I know the quantum computer actually got it right?
It is the fundamental verification bottleneck. If the machine is objectively smarter than you, how do you grade its test?
Right. Maybe it just guessed. Or maybe a cosmic ray hit the processor halfway through and it just confidently handed me a string of random numbers. It's like an AI chatbot hallucinating a completely fake legal citation.
Traditionally, the only rigorous answer has been to build a second, equally powerful, fully trusted quantum computer to double-check the first one's work.
Which is financially absurd. That's like buying a second multi-million-dollar sports car just to make sure the speedometer on the first one is calibrated correctly.
Exactly. Or you'd need a functional quantum internet to securely link remote machines together, which doesn't exist outside of very small lab demonstrations. This is why the Giustiani paper from late 2025 is such a milestone. They developed a protocol for on-chip verification.
Checking the homework without needing a second brain in the room.
Precisely. You don't need a separate verifier. They demonstrated this practically on the Quantinuum H11, which is a trapped ion quantum processor. Their method relies on a clever game of hide and seek.
The paper called them trap rounds, which sounds very ominous.
It's highly descriptive. The concept is to break the computer's overall workload into two distinct types of operations: computation rounds, where it's actually churning through the math you care about, and test rounds, which are the traps.
And the quantum computer has no idea which round is which.
That is the cornerstone of the protocol. It's a form of blind quantum computing. The server, the quantum machine itself, is totally blind to the difference. During a test round, the client, that's us, inserts trap qubits.
Okay.
These trap qubits are prepared in a very specific, secret state where we know exactly what the final measurement outcome should be if the computer is executing its gates honestly and flawlessly.
So if I weave a trap into the computation that I secretly know must result in a 1 and the computer hands me back a 0, I immediately know the machine is compromised.
Exactly. And because the computer cannot distinguish the trap qubits from the real data qubits, it cannot cheat. It can't decide to be lazy on the difficult computation rounds, but suddenly perform perfectly on the test rounds. If the hardware is drifting or if the error rates are spiking, it will inevitably trigger the traps.
And they ran this on actual hardware, not just a simulation.
Real hardware. They executed a measurement-teased quantum computation, or MBQC, using a highly entangled state called a cluster state with 52 vertices.
52 vertices.
Yes. It represents the largest verified MBQC computation ever performed to date.
But there's a massive caveat here, right? Because nothing is ever that simple in quantum information, I recall a whole section in the paper harping on something called secret independent noise.
It sounds like espionage jargon, but it is mathematically critical. The entire trap protocol falls apart if you don't have secret independent noise.
Break that down for me.
Think of it like a high-stakes game of poker. You are the client, holding your cards. Those are your secret traps. The quantum computer is the opponent sitting across the table.
Okay, I thought...
If the opponent can read your physical tells, if they know you blink differently when you're bluffing versus when you hold a royal flush, they will beat you every time. In this context, secret independent noise means the quantum hardware has absolutely no tells.
So the noise inside the machine can't fluctuate based on the secret parameters of the trap.
Exactly. The background error rate, the static cannot change simply because you decided to insert a trap qubit instead of a regular data qubit. If the machine hummed at a slightly different frequency, or if the thermal dissipation changed specifically when a trap was present, the blind verification would fail. The computer would essentially smell the trap.
It has to have a perfect mechanical poker face.
Yes. And to ensure that, the researchers had to perform exhaustive quantum state tomography. They basically took a full 3D diagnostic scan of the quantum states to mathematically prove that the H11 processor's noise profile was utterly blind to their secrets.
They proved the poker face was real.
They did. And once that assumption was validated, the trap game worked flawlessly. They ran a Grover's search algorithm and a CNOT grid. In both cases, the failure rate during the test rounds consistently stayed well below the 25% threshold.
Why 25%?
That's the mathematical cutoff for this specific protocol. If the test failure rate stays below that line, you can mathematically guarantee the integrity of the actual computation rounds.
So we can finally trust the answers these machines give us as they scale up without needing a shadow machine to audit every single step. Trust, but rigorously verify.
Exactly. It's a massive leap forward for the viability of cloud-based quantum computing.
Let's try to pull all these threads together because we've covered a ton of ground today. We started with the sheer physical nightmare of the interconnect bottleneck.
Millions of wires threatening to boil the dilution fridge.
Right. And we saw that Lee and his team solved it by looking backward to mechanical MEM switches, discovering they love the deep freeze, and adapting them with clever breaking waveforms so they wouldn't bounce themselves to pieces.
The soft landing.
Then we completely shifted our view on computation itself with the Nyingen paper.
Finding that for incredibly complex optimization problems, we shouldn't fear the environmental noise, we should harness it. By violently shaking the mathematical box with shot noise, Dirac 3 found better answers using significantly less energy.
And finally, we tackled the trust issue with Giustiani's work.
Embedding cryptographic lie detector tests directly into the quantum circuits, using hidden traps to force the machine to prove it's operating honestly.
It really feels like we're witnessing a distinct maturity phase in this field. Even just a few years ago, the big headlines were all breathless announcements like new qubit discovered or quantum supremacy achieved on toy problem. But these three papers, they feel different.
They are definitely a new era. This is the painful but necessary transition from brilliant science experiment to robust industrial machine. When you're building a bespoke prototype in a university lab, you don't lose sleep over wiring bottlenecks or blind verification protocols. You just want the physics to work once. But you desperately worry about those things when you're trying to build a commercial product that needs to run flawlessly for a decade.
It's the unsexy stuff that actually makes the technological revolution happen. It's not just inventing the internal combustion engine. It's designing a reliable transmission so you can actually drive the car.
If we connect this to the overarching narrative of the industry, it clearly tells us that the quantum future isn't simply about cramming more qubits onto a piece of silicon. It's about these highly clever engineering workarounds.
The plumbing and the protocols.
Exactly. Engineered waveforms, photonic feedback loops, and cryptographic traparounds. That is how we actually get to a reliable million-qubit machine.
I have to say, the whole entropy computing concept is really sticking with me. The idea that operating at a lower power state, being more energy efficient, might inherently make a system smarter at navigating complexity. There is definitely a broader life lesson buried in there somewhere.
It is a deeply provocative thought to leave on. The Dirac 3 results strongly imply that low power doesn't just save on the electricity bill, it fundamentally creates the necessary environment for innovation.
Because it allows for the noise.
Right. The noise prevents stagnation. It forces the system to keep exploring. It really makes you wonder, maybe the ultimate future of supercomputing isn't pristine, energy-hungry perfection. Maybe the future is low power, chaotic, and dynamically self-correcting.
I absolutely love that. And I also love the very practical lesson from the MEMS switch. Sometimes when you're moving incredibly fast and you feel like you're about to hit a wall, you don't necessarily need to stop what you're doing.
You just need to tap the brakes.
You just need a perfectly engineered waveform to stick the soft landing.
A perfect analogy.
Well, that is all the time we have for today's discussion. Thank you so much for guiding us through the frozen wires and the helpful chaos.
It was my absolute pleasure.
And thank you for listening. Look for the bounces in your own life this week. You've been listening to The Deep Dive. We'll catch you next time.